Hello, you're welcome to today's physics calculation. Now, before we go into this, I'm very sure that you have an understanding of what physics is. Physics is a physical science, it's a kind of pure science. So, before we go into today's exposition, I would love you to know a couple of things. If you don't have a basic understanding of what physical quantities are, because when we talk about physics, we're talking about physical quantities, quantities like velocity, time, acceleration, and so on and so forth. I would love you to go ahead and go ahead and study them. It's very, very important. Go learn the various physical quantities. Most times they are divided into fundamental and derived, and learn them, then come back to the zero exposition. So today we're going to be looking at mechanics. You're looking at mechanics today. Now, mechanics is a branch of physics which deals with the force acting on various masses of bodies. So when we talk about the force that act on various masses of body that bring about various sort of things such as movement, change in shape, change in direction, then it means you're talking about mechanics. So mechanics is a very, very broad part of physics. So when we talk about mechanics, mechanics is divided into two parts, and the very first part is what we call the statics, and the next part is what we call the dynamics. Statics and dynamics. Now, when we talk about statics, what is statics? Statics is a part of mechanics that deals with bodies at equilibrium. We're talking about bodies at equilibrium. We're talking about bodies at rest. Now, when I say a body is at rest, it's not like there are no movement, but all the network of forces, acting on the body, on that very body to bring about movement, cancel out one another. For example, a table with four legs. A table with four legs, when you say table with four legs, it looks like the table is not moving, but all the four legs cancel out the network of forces. So that's that for statics. So statics deals with bodies at equilibrium, bodies are not moving. That's what statics is. That's what statics is, I mean. So the next we have there is dynamics. Now when you talk about dynamics, dynamics simply deals with bodies in motion. Now for dynamics, unlike statics, dynamics, we talk about bodies in motion like a car moving and airplane, bodies in motion is what dynamics is all about. So today we are going to be focused on dynamics. You talk about statics in a later exposition. Now, when we talk about dynamics, dynamics is broken down into two parts, which are the kinematics and the kinetics. Kinematics deals with the geometrical layout of bodies in motion. Now, when we talk about kinematics, we are not talking about the force that puts such a body in motion. So under kinematics, we deal more with the dimensions of bodies in motion. We're talking about the geometrical layout of bodies in motion. So we're not talking about the force that put the bodies in motion. So why for kinetics? Kinetics, we are mainly concerned with the force that put a given body in motion. So today we're going to be looking at kinematics. So under kinematics today, we're going to be focused on what we call the one-dimensional rectilinear motion. The one-dimensional rectilinear motion. Now, when we talk about rectilinear motion, rectilinear motion is a kind of motion which is simply the motion of a body in a straight line. When we talk about rectilinear motion, we're talking about bodies moving in a straight line from one point to another. So when we talk about one dimension, now look at this. This is a straight line motion of bodies either along the x-axis, acceleration from rest, or along the y-axis, acceleration of bodies under gravity. Now, when we talk about one-dimensional rectilinear motion, as you can see, we've talked about what rectilinear is. Rectilinear simply means the bodies are moving in a straight line. Now for one dimensional, it means the body is moving in one dimension. Either the body is moving along the y-axis, which is for either falling bodies or rising bodies, or the body is moving along x-axis, which is for bodies just moving, acceleration of bodies from rest. For example, a car moving on the street, a bicycle rider, a motorcycle rider, all those kinds of motion are, they are mainly motions along the x-axis. But for objects that are falling or objects that are floating in the air or rising up, there are motions of bodies along the y-axis. So today we're going to be using the velocity time graph to, shed more light on this. We're going to be using this very time graph to get a couple of formulas under our equations of motion. So as you can see, this very graph along the y-axis is what we call the velocity, which is in meter per second. Then along the x-axis is what we call time, which is in seconds. Now this body is the rest point, but this body did not really start moving from rest. The body took off, accelerated from this very portion. This is initial word, speed or initial velocity, accelerated from here to this place. So over this time. So there's the initial velocity. That means the body moved earlier on from this point to this point before it then changed its velocity from here to here. Now, if there is no change in velocity, there can be what we call acceleration. So average acceleration is the change in velocity of a body over time taken. And that's why I said at the very beginning of this very exposition that in your own best interest is you have to understand some basic things, rudiment on physics, physical quantities, and so on and so forth. So I'm very sure you did that. So let's go. So you're going to be deriving the formulas for the equations of motion. That's what you're going to be doing first. Don't forget this. A body accelerated from this very point up to this very point. This is the initial velocity of the body. As you can see from here, look at the measurement, the dimensions. This is what we call kinematics, because you're not talking about force, you're just talking about the general geometry of motion. So from here to here is initial speed or initial velocity, while from here to here is the final velocity. So if here to here is initial velocity and here to here is final velocity, it means here to here is change in velocity. This was where acceleration took place, from here to here. So why there's the time. So let's see. We're going to be deriving the equations of motion. So the first we have is average acceleration or acceleration. Don't forget, acceleration is a vector quantity. Acceleration is equals to change in velocity over time taken. So change in velocity is final velocity minus initial velocity over time taken. So acceleration, velocity itself is a vector quantity, time is a scalar quantity. Acceleration is final velocity, the v is final velocity. Final velocity, that's what the v is. The u represents initial velocity. Final initial velocity, while the time represents, the t represents the time, which is in seconds. The a represents acceleration. I'm doing this for those that don't have a basic understanding of a basic knowledge of this. So v represents final velocity, u is initial, t is time, a is acceleration itself. So the next thing you're going to do, don't forget the formula for acceleration or average acceleration is change in velocity over time taken. So change in velocity means final velocity minus initial velocity. That's what we have right here over time. So the next thing we do is to cross multiply. So a times t is at equal to v minus u. So you color your like terms to send the initial velocity to the other side. V is u plus at. There's the first equation of motion. Now we're going to be using this very equation of motion for our one-dimensional motion. So that's the very first. So the next thing we're going to get now is we're going to get what we'll call the total distance traveled by the body. Now, how do we get the total distance traveled by the body? Don't forget formula for velocity. Velocity is displacement or distance moving in a specific direction. Don't forget velocity and speed, they're almost the same thing. The difference is that one is a vector quantity, that is velocity, while speed is a scalar quantity, that is it doesn't move in a specific direction. The difference is that one moves in a specific direction and the other one does not. One is scalar, one is vector. So velocity is displacement s over time taken, or distance over time taken. So now for me to get my distance, it means I have to do velocity times time taken. So distance is velocity times time taken. So if I look at my velocity time graph right here, this is velocity, this is time. So if I'm going to multiply velocity and time together, it means we're doing something that looks like area of a shape. So if you look at this very old setup, this geometry, this plane shape, I have a rectangle and I have something that looks like a triangle. So altogether here, I have a trapezium. I have a trapezium here, or a trapezoid. This is what I have here. So this is a rectangle, this is a triangle, together make a trapezium. So if you're going to say velocity times time, it means you're going to be getting the area of this shape. That's what it means. So when we talk about distance is simply the area of a trapezium. So what's formula for area of a trapezium? Area of a trapezium is equals to 1 over 2 open bracket a plus b times height. 1 over 2 open bracket a plus b times height. That's the formula for area of a trapezium. So it's very important that you have a basic understanding of mathematics for you to understand all what we're doing right now. So Don't forget that this is equals to the total distance traveled by this very body that carried out that sort of acceleration. So distance now is 1 over 2. Now what is A? A is the initial velocity. Look at the A here. This A, this is B, the longer side. A is initial velocity, B is the final velocity. So A is U, the final velocity, which is B, times height, which is time. So S is V plus U, this over 1, times time. So this is our second equation of motion. It's our second equation of motion. So having gotten these first two equations of motion, we will move on to the next we'll move on to deriving the next set of equations of motions. So the very first one, as you can see here, v equal to u plus at, that's equation 1. The second equation is s equal to v plus u over 2 times time. Don't forget that s is the displacement or distance, the v is the final velocity, u is initial velocity, t is time taken, a is acceleration. So what we're going to be doing right now, we're going to be using our mathematics skills, understanding subject of formula and so on and so forth. We're going to be doing that, substituting a couple of things into the other to get the other equations of motion. So v equal to u plus at, we're going to substitute it into equation 2. So v equal to u plus at. So what's going to be then? That'll be s equals to, now anywhere I have my v, I'll put my u plus at. So that'll be u plus at, then plus u over 2. Then times the time out here. So s equal to u plus at plus u. Don't forget that the u plus at is the same thing as the velocity right up here. B is u plus at, u plus at. So s, now we collect our like terms. Let's open up the bracket and bring the u's together. So u plus at over 2 times time. So s is u plus e is 2u plus at over 2 times time. So s is, now those two could divide them. Basic knowledge of fractions. 2u divided by 2 plus at over 2 then times time. So what do we have there? S, 2 cancels 2, u plus at over 2 times time out there. Now we're going to open up the bracket. You open up the bracket. So that'll be s equals to t multiplies the stuff inside the bracket. U times t is ut plus at times at over u. 80 over 2 times t is 80 squared over 2. So s is ut plus half 80 squared. This is the next equation of motion. There's the next. So quickly, you're going to derive more equations of motion. Now, the next thing we're going to do is we're going to make the use of the formula to derive the fourth one. If v is equal to u plus 80, now let's make the use of the formula. So v is equal to u plus 80. So u is going to be v minus 80. That's what the u is. V minus 80. So you're going to fix in this u equal to v minus 80 into equation 2. Equation 2 is the reference point for virtually all other derived equations of motion. So you're going to be fixing in the u equal to v minus 80 right in here. So that will be s equals to v plus the u is what? V minus 80 over 2 times time, that's times t. So s is v plus v is 2v minus 80 over 2 times time. So s is, share the stuff out, 2v minus 80 over 2 times time. Then s is v minus 80 over 2 times time. Then s is vt minus 80 squared over 2. S is vt minus half a t squared. So that's that. Don't forget, s is equal to v plus v minus 80 over 2 times time. Now, what did we do? We made u equal to v minus 80 the sort of formula. Then what we did next was to pick it up and fix it in this very equation 2. So where we had an s equal to u plus s equal to v plus u over 2 times time. Now we fixed in our u equal to v minus 80. We fixed it in, so that will be v plus v minus 80, then over 2 times time. So I collected our like terms. V plus v is 2v minus 80 over 2 times time. We share the 2 out, so that is 2v over 2 minus 80 over 2. Close the bracket. So s divide v minus 80 over 2 times time. Then we did this. We open up the bracket. S equals to Vt minus At squared over 2. And we arrived at this. So that's the fourth equation. So we're going to be seeing the fifth equation, and that will be probably the final equation. So we have our four derived equations already. V equal to u plus at equation 1. S equals to v plus u over 2 times time, equation 2. S equal to ut plus half eta squared, equation 3. S equal to vt minus half eta squared, equation 4. Now we're about to derive the very last equation, which is the fifth equation. And now don't forget, those first two equations are very, very important to derive all those equations. We got these and these from this first two equations. So we're going to get the fifth one also from this very first equation. So which of them are we going to make out of formula this time around? We made v was substituted into this, we got this. U was substituted into this, we got this. Now we're going to substitute t into this to get the last equation. So let's go. So if you have v equal to u plus at, I want to make this sort of formula. It's very important you have a knowledge of sort of formula for you to understand what we're about to do or what we've been doing. So that will be v minus u equals to at divided both sides by a. Then the time is v minus u over a. So t is got to v minus u over a. So I'm going to bring it back here, right here. So s got to v plus u over 2 times time. Then the distance right now will be v plus u over 2 times, what's the time? The time is v minus u over a. We're going to be doing something like this. We're going to expand. We're going to be expanding the table. You need a knowledge of expansion also. If your mathematics is not decent, you'll struggle to understand what I'm doing right here. So v plus u times v minus u over 2 times a. Just right under. So the next thing we do is s equals to expand, open up. V times v is v squared minus vu plus vu minus u squared over 2a. So what do we do next? S is minus vu plus vu goes out. That will be v squared minus u squared over 2a. So what do we do next? We cross multiply. That will be 2as equal to v squared minus u squared. So what do we do next? We send this stuff right here. That will be v squared equal to plus u squared plus 2as. This is the last and final equation, the fifth one. So right here we have all our 5 equations of motion. So you have to learn all those things. I would love it if you could learn how to derive all those formulas. But if you find it hard to derive them, just look for a way to put them upstairs, because you're going to be using them in the next set of expositions. You're going to be solving all kinds of questions on that rectilinear motion. And don't forget that, as I said, motion or mechanics is divided into 2 major branches, which are the statics and the dynamics. The statics and the dynamics. When I mean statics, I mean statics and the dynamics. Now we've been working on the dynamics. The dynamics are broken down into 2 major parts, which are, as we said, the kinematics and the kinetics. So we're right now working on the kinematics. So at this point, we're going to draw the content of today's exposition. If you found this resourceful, subscribe to this very channel and share this exposition. Thanks.